It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging GATE contest engineered to give you an experience like none other.
Where you put your knowledge to test
and battle it out with a test
To bring out the best in you, Unacademy Combat is the most competitive, gamified contest for GATE till date, with the best of the questions by best educators.
with detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack GATE deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate GATE challenge. Unacademy Combat. Register now.
Hi, hello, good evening all. Welcome to Unacademy. Let me introduce myself first, then after we will discuss about the content in this session. My name is Banu Prakash, expert in GATE and ESE. I did MTech from NIT Kurukshetra. I have 10 plus years of teaching experience and I train many students throughout our country for different competitive exams like GATE, ESE and many more PSUs. I expertise in the subjects of electrical machines and power electronics. BPC 10 is my referral code. So use this code, you will get 10% to discount on Plus subscription and Iconic subscription. Let us know about what are the benefits of the Plus and Iconic subscription. By taking Plus subscription, you can get live classes from the top educators, okay, and also you can get structural schedule, unlimited practice questions and test series. The live classes means, so that is a we have a we will get more number of the teachers, or many more number of teachers for each subject, so that you can select the teacher as per your choice for each subject. And also you can get proper schedule, the structural schedule for 6 months, 3 months, 12 months and 24 months. And another one, unlimited practice questions based on the topic wise and also subject wise. And one more benefit of the plus subscription, that is the test series. So it is a very important for any competitive exams. So we will provide the some test, and by the test series you can analyze your performance week by week, so that you can improve wherever you are lagging, then you can improve your weakness. So our weakness points and lagging points here. And one more subscription, that is iconic subscription. By taking iconic subscription, so you can get all these four benefits. In addition to these, so you can get personal coach, study planners, expert guidance and ESE mains questions and answers. Personal coach means it is one-to-one guidance for your GATE, ESE and any PSU's exams. And you will get the proper study planners and expert guidance, ESE mains questions and answer. So if you write the ESE exam, then it is a very useful for your GATE and ESE preparation. So my point of view, iconic subscription is the best thing for your preparation of any competitive exams. So just do one thing. If you want to take the subscription, use my code BPC10. Okay, it is my referral code. Use this code, you will get 10% to discount on plus subscription and also iconic subscription. And what about the what about fee structure of the iconic and plus subscription? So fee for the plus and iconic subscription, so this plus subscription is available for 12 months, 18 months and 24 months. So for 12 months fee is 27,225 rupees, and for 18 months fee is 34,650 rupees. Okay, and another one for 24 months fee is 39,600 rupees. Okay, got it? And one more subscription, that is iconic subscription. It is available for 12 months and 24 months. So for 12 months fee is 45,225 rupees. For 24 months fee is 66,600 rupees. Okay, and another slide, this is the how to install Unacademy learning app. So it can be installed, so by search, initially search the Unacademy learning app in your Play Stores, and after that install this app. And after the installation, and access pre-special classes taken by the top educators. The code is asking to access the class. Use my code, that is BPC10. Okay, it is an invitation code for the pre-special classes, and also it is a referral code to get the 10% to discount on plus subscription and iconic subscription. Okay, and this is the month January month schedule of Unacademy GATE English channel. So communication system from 9 to 10 a.m. Engineering mathematics 10 to 11 a.m. Okay, analog electronics 4 to 5 p.m. and foundation course for mathematics for GATE 2022 and 23 students, so 5 to 6 p.m. So next one, foundation course for aptitude, okay, for GATE 2022-23, 6:15 to 7:15 p.m. And next one, this is the measurement subject for Genco, Transco, SSC, RRBEs, so from 7:30 p.m. to 8:30 p.m. And electrical machines for Genco, Transco, Discoms, okay, SSC, JE, RRB, JE, from 8:30 p.m. to 9:30 p.m. Okay. In previous class we had discussed about what is meant by the transformers and what are the applications of the transformers, and also we have discussed about what are the features of the transformers. Okay, first one, we had discussed about the definition of the transformer part. Okay, and after that we discussed about applications of transformer, and then after we had discussed about the features of the transformers. Okay, primary function of the transformer, mostly transformers are used in the electrical power system to change voltage and current levels from the sending end to the receiving end of the power system. And some other applications also there. In electronic circuit, transformer is used as impedance matching device to transfer the maximum amount of the power through the load. Okay, and another one, it is also used for the isolation purpose. Okay, and what are the features of the transformers we have discussed in the previous session, and that is one is it is a constant power device, constant flux device, constant frequency device. So it is 180-degree phase shifting device. Okay, it is treated as a two-port network. Transformer is a electromagnetic energy conversion device. And what about definition of the transformer? The transformer is a static device which transfers electrical power from one circuit to another circuit at same frequency. Okay, so all this the part we had discussed in the previous session. So today we will discuss about another one, so that is operating principle of the transformer, and next one, working of the transformer. Operating principle means what is the exact principle of the transformer to work, and working of the transformer means how does EMF induce in the windings of the transformer. So this part we will discuss very clear in this session. So first one, we will discuss about operating principle of the transformer. So initially we have a question. So that is, what are the basic requirement to induce the EMF in a transformers? Okay. So this is a basic requirement to induce the EMF in a transformer's part. So first requirement is this first part, the stationary magnetic field. Got it? And second requirement is a set of conductors or group of conductors. Got it? And third requirement is that is a relative time variation. Between magnetic field and set of conductors. Okay, so these are the basic requirement to induce the EMF in a transformer winding. The first one is stationary magnetic field, second one is a set of conductors or group of conductors, and third one is relative time variation between the magnetic field and set of conductors. Okay, good evening all. Ramakrishna. Yeah, I'm good. How are you? So these are the basic requirement. One is a stationary magnetic field, set of conductors or group of conductors. Third one is relative time variation between the magnetic field and set of conductors. Got it? So next one is what is the operating principle of the transformers? So before that we have a question. What is the mean by relative time variation? So that is a flux produced in the transformer is a time varying nature of the flux. So that phi of t is equal to, okay, here phi of the t equal to, so it is a phi maximum is a sine omega t here. So flux produced in the transformer is a stationary but varying with the time. As the time changes, the flux is also the changes here. So this is known as a relative time variation between the magnetic field and set of conductor. So this magnetic field is a stationary. Okay, this is the magnetic field. The stationary means the speed of the magnetic field. Okay, here speed of the magnetic field is equal to 0. There is no the speed. It is not a rotating magnetic field. So simply a magnet is there. For example, so we have a one magnet. So always what will happen? So within the magnet, flux lines are passing from the north pole to the south pole. So this is the direction of the flux lines within the magnet. And outside the magnet, what will happen? So this is the direction of the flux lines always. So flux is always flows from the north pole to the south pole. All of you got it, point? So this is this type of magnetic field is known as a stationary magnetic field. That is the speed of the magnetic field is equal to 0. So in order to induce the EMF in the AC machine, for example, generators, okay, or synchronous generator and induction generator, rotating magnetic field is required. So that we will discuss later. But here in case of the transformer, so which type of magnetic field is required? The stationary magnetic field. And second one is a set of conductors. So what is the meaning of set of conductors or group of the conductors? So that means it is a winding. Okay, this is some winding is suppose it is a core here. So we have winding is provided on the limb. So this is the group of the conductors or set of the conductors. This is also required. So magnetic field, the set of conductors, and third requirement is the relative motion between the relative time variation between the magnetic field and set of conductors. Okay, so this is what is the meaning of relative time variation? The flux produced in the transformer must be varied with the time. Okay, and stationary and must be varied with the time. This type of magnetic field is known as the relative time variation between the magnetic field and set of conductors. Okay, all of you got it? So next one, we have a question. Exactly what is the operating principle of the transformer? So transformer operates on the principle of Faraday's laws of electromagnetic induction. That is a Faraday's law of electromagnetic induction. Okay, so it is a second law. We have two laws. One is the Faraday's first law and also Faraday's the second law. So the transformer operates on the principle of Faraday's laws of electromagnetic induction. And what is the statement of this Faraday's laws of electromagnetic induction? So it states that an EMF induced in a transformer, okay, is direct EMF induced in the coil or winding is directly proportional to rate of change of flux linkages. Okay, so it states that an EMF induced in a coil or winding is directly proportional to rate of change of flux linkage. Okay, rate of change of flux linkage. Got it? So mathematically, how do we represent? So that is a EMF, okay, E of t, okay, E of t directly proportional to the rate of change of the flux linkages, okay, flux linkage, okay, dψ by dt. So E sometimes you can write directly in the small letters, okay, E is a directly proportional to rate of change of flux linkages here. So this is a the proportion, the E is a directly the where psi in the sense, okay, what is the psi here, where psi is a flux linkage. So what is the meaning of flux linkage? So this is equal to number of the turns of the winding. Okay, N is nothing but it is a turns of the winding multiplied by flux in the winding, phi of t values here. So therefore you can write E of t is equal directly proportional to, so differentiation of the here N of phi of t, so with respect to the time. So here N is a some number, it is a some finite value. So if you remove this constant, proportionality constant here, so E of t is equal to minus N, so phi of t, the differentiation of the flux with respect to the time. So this is a here EMF induces in the coil according to Faraday's laws of electromagnetic induction. So now we have a question. So what about this minus sign? Okay, here. So where minus sign indicates, okay, this minus sign indicate direction of the induced EMF. So magnitude is equal to, magnitude point of view, E is equal to, so that is the N d phi of t by dt. Okay, this is, so N is the number of the turns. But how does, what is the here? It is a vector quantity, so that we have to specify the direction as well as the magnitude. This is the direction of the magnitude here. This minus sign indicates the Lenz's law. So according to the Lenz's law here, so this here EMF opposes, okay, this opposes applied voltage V1. So this the V is the opposes applied voltage, okay, V1 in the transformers. So that is a to satisfy the Lenz's law. Okay, is that clear, everyone? So I repeat once again, listen. What are the basic requirement to induce the EMF in a transformer? First requirement is stationary magnetic field. Second one is set of conductors. Third one is the relative time variation between the magnetic field and set of conductors. Okay, and similarly, and transformer operates on the principle of the Faraday's laws of electromagnetic induction. So what is the statement of the Faraday's laws of electromagnetic induction? An EMF induced in a coil is directly proportional to rate of change of flux linkage. So mathematically we can write E is a directly proportional to rate of change of the flux link. So what is the meaning of flux linkage? How much amount of the flux links with the number of turns of a coil, that is known as a flux linkage. So now if here N is a constant, so here if we remove this proportionality constant, we will get N d phi by d. But here minus sign indicates, okay, what is the meaning of minus sign? Minus sign indicates Lenz's law, okay, or this is the Lenz's law. We will discuss very clear about Lenz's law. So we have a question about what is the statement of the Lenz's law and how do we apply the Lenz's law in electrical machines. Okay, this is a very important point. Okay. So Lenz's law is the effect opposes very cause producing it. Okay, suppose in a coil we have taken, so this is the one coil, got it point? So it is the one magnetic core, and we are placed some winding on the core like this, okay, which has some number of the turns n. So it is the here magnetic core, and this is the winding on the core which has n number of the turns. Example point. So it is excited with, okay, this is the excited with the supply. Okay, this supply, the here excited with the supply of V of t. Okay, so when it is excited, then what will happen? The current passes through the coil. Okay, here I of t. So due to this, suppose we have a question. Just imagine current entering this position. Okay, current entering here on the top of the core. Okay, that's why we have represented with the cross mark, and this one is represented with a dot mark. So due to which what will happen according to the right hand thumb rule. So if the orientation of the fingers represent the flux direction, the here orientation of the finger represent the current direction, this thumb indicate the flux direction. So that flux lines are, okay, this is the direction of the flux, right? So flux here. So this flux induces the EMF in the winding. Okay, EMF in the wind. So now which one is the effect here? So this is the applied voltage is a, just imagine there is no applied voltage in a coil. So what will happen? No current passes through the winding, and also no flux created in the core, and after that there is no induced EMF in a coil. So all of you got it point? Suppose here is a first one, applied voltage V of t is given to the coil. So magnetizing current flows through the transformer, okay, flows to the winding, and after that here this is the flux will be created. So according to the Faraday's laws of electromagnetic induction, this EMF induces in a coil. Okay, this is the V of t here. So what, just imagine there is no applied voltage in a coil. So what will happen? No current flows to the coil, no flux created, no EMF induced. Okay, am I right? So now how do we define this law? What Lenz's law states that, so this induced EMF, because induced EMF in a coil because of this applied voltage. Okay, because of this applied voltage. So that's why this induced EMF opposes applied voltage, to satisfy the Lenz's law. So that how do we, what is the statement here? The effect opposes, okay, here effect opposes very cross producing it, very cross producing it. Okay, this is the statement. So that's why here EMF induced in a coil. So VMF here effect is a, which one is the effect here? The effect is a EMF induced in a coil. So which is the cause? Okay, cause is a applied voltage, the V of t. So this E of t opposes applied voltage, to satisfy Lenz's law. Okay, got it point? So EMF induced in a coil opposes applied voltage to satisfy the Lenz's law. Okay, so by using this statement, what we conclude here? So EMF is a voltage quantity. Am I right? So this is the voltage quantity. Okay, and applied voltage also, that is a voltage quantity. Got it point? So EMF is a voltage quantity and applied voltage also voltage quantity. So that according to Lenz's law, okay, here according to Lenz's law, okay, so this first statement, so if effect is a voltage quantity, effect is voltage quantity, then cause would be voltage quantity only. Okay, similarly, so if effect is a current quantity, second one, suppose if the effect is current quantity, then what will happen? The cause would be current quantity only. Current only. Okay. The another one, suppose if effect is, okay, effect is flux quantity, okay, then the cause would be, okay, cause will be the flux quantity only. So that means, so flux opposes the flux, current opposes the current, and another one, voltage opposes the voltage quantity only to satisfy the Lenz's law. Here EMF cannot oppose the current, so EMF cannot oppose the flux. Only EMF induced in a coil opposes the voltage quantity. So to get this cause, so that's why EMF induced in a coil opposes the applied voltage to satisfy the Lenz's law. Okay, so this is the statement of the Lenz's law. The effect opposes very cause producing. Okay. So now let us discuss about working of the transformers. Okay, so what is the meaning of working? Working of the transformer means how does EMF working in the sense, so that is a how does EMF induce in transformer windings. Okay, this is the meaning of working of the transformers. So let us take example point. So here this is the transformer core, okay, which has the low reluctance and high permeability. Okay, mu is a permeability here. So this is the call, suppose in a core, okay, this length is not, this is a, this part is nothing but, okay, it is a area of cross section of the core. Okay, this is the area of cross section of the core. So next one, what about the length here? Okay, this is the length. Okay, this complete part from ear to ear. So this is a length of the core. Just wait a minute. Okay. So now from here, okay, this is the complete, it is a length of the transformer core, and we know that it has a two major parts. Okay, major parts of the transformers. So what are the major parts of the transformer? So one is a transformer core part, and second one is a transformer windings. So that is a LV winding and HV winding of the transformers. So all of it clear? So let us place the winding. So this is a winding of the transformer. Okay, one winding like okay, this winding as N1 number of the turns. So which is excited with the supply of V of T. So that is the single phase AC supply. AC supply, it is a V1 of T. Okay, that alternative nature of the supply or time varying nature of the supply. That's why we have written as the V1 of the T. Now similarly, the another winding which is placed on the limb as shown in the figure. Okay, like okay, this is the secondary winding of the transformers. Okay, so what is the meaning of working in the sense, how does EMF induced in the transformers winding? So where N1 is a number of turns in the primary winding, where N2 is a number of turns in the secondary winding. So therefore let assume, okay, let N1 is the number of turns of the primary winding. Okay, and where N2 is a number of turns of secondary winding. Got it my point? N1 is a number of turns in the primary winding, where N2 is a number of turns in the secondary winding. So what will happen whenever whenever transformer is excited with the AC supply? Okay, whenever transformer is excited with the AC supply, the time varying nature of the current passes through. Okay, current passes through the winding I of T. So this is the magnetizing current. So this current enters at this position, okay, like this, okay, enters here, and this is the leaving position. Okay, here is a leaving, is a dot in the means the entering position, the cross is the leaving position. So just apply the right according to the, this is the direction of the current. So current passes to the number of turns of a coil, MMF set of initial, and thereby flux will be created. So this flux is created here. Okay, this flux pi 1, the created in this winding. So how do we obtain this direction of the flux here? This direction of the flux that can be obtained, okay, by using right hand thumb rule. So according to the right hand thumb rule, this is the current orientation of the fingers represent the current direction, then thumb indicate the flux direction. So that flux lines are, okay, from bottom to upward direction. So whatever flux produced in this coil also links in the secondary winding through transformer core. Okay, like this. Okay, this is a, so this is the secondary winding of the transformers. Okay, all of it clear? So first point, whenever the transformer is excited with AC supply, time varying nature of the current, okay, nature of current passes through primary winding turns. Okay, primary winding turns and MMF, okay, primary winding turns. As a result, MMF, magnetomotive force, MMF set off, and thereby, okay, and thereby, okay, flux will be created. Okay, this is a very important statement. So whenever transformer is excited with the AC supply, time varying nature of the current passes through the primary winding turns. As a result, MMF setup and thereby flux will be created. So now we have a question. How does flux creates in the winding? How does flux create in winding or coils? Okay, how does flux create in the winding of the transformers? Okay, this is the one of the question. So we know that according to, okay, suppose, so we have a one conductors. Just let us take one conductor. Okay, this is the conductor. Got it point? So which has a length of the conductor, this is the length of the conductors. Okay, and area of the cross section. Okay, this is called area of the conductor, and this is the length of the conductors. Suppose when conductor is excited with the supply, then what will happen? The current passes through the conductors like this. Okay, so this is the direction of the current, right? Okay, this current passes through the conductors, conductor like this. So according to this is the called the current in the conductor I. Okay, I amount of the current passes through the conductors. So whenever a current passes through the conductor, there will be the magnetic field around the conductors. So according to the Ampere's law, a current carrying conductor produces magnetic field around the conductors. Suppose there is a magnetic field like this. Okay, this is the completely, it is the one magnetic field the around these conductors like so on. So this is the direction. How do we obtain the direction of the magnetic field? So it can be obtained by using right hand thumb rule. So this law is known as, okay, it is a Ampere's law. Okay, Ampere's law. Okay, so what it states, the statement of Ampere's law, it states that, okay, it states that a current carrying conductor produces magnetic field around it. Okay, around it. So how do we obtain this direction of the magnetic field? So where direction of magnetic field, direction of flux can be obtained by right hand thumb rule. Okay, all of you clear point? So where current carrying conductor produces magnetic field around it. So that direction of the magnetic field can be obtained by using the right hand thumb rule. The same principle we have applied here. So this is the current carrying conductor. So this current carrying conductor produces the magnetic field around it. So this direction of the magnetic field can be obtained by using, so which law? Right hand thumb rule. So according to this Ampere's law, so this direction you can obtain by using right hand thumb rule. So what about the magnitude? So mathematically, so this is a integration of, okay, integration from 0 to L. So integration over the length. So the from magnetic field intensity, okay, H is nothing but magnetic field or magnetizing force. the HDL according to Ampere's law. Okay, Ampere's law, mathematical form. So that is equal to current passes to the conductors. So this is for the single turn. Okay, only for one turn coil. One turn coil. Got it? Suppose we have a n number of the turns. Then how do we obtain here? So integration from the 0 to L, the HD magnetic field intensity, some n number of the turns. Okay, this is for the n turn coils. Okay, got it point? So this is the n turn coil. So where H is called, okay, this is law is a Ampere's law. So where H is called, H is a magnetic field intensity. Magnetic, the field intensity, got it? And where N is a number of the turns. Okay, number of the turns. Okay, and suppose, so this is a I is the current passes through the conductor. Current passes through conductor or through windings. Got it point? So this is the current passes to the current. So now let us apply the integration here. So complete integration. H is the some constant magnetic field intensity. So that H, okay, integration over the length from 0 to L. So dl the equal to n multiplied by I. Okay. So where I, this is the I, current passes to the conductor, where n is the number of the turns. So then apply the integration, you will get H is equal to H into the length of the conductor or core. Okay. So now this is equal to number of turns of the winding, and current, which current here? It is the magnetizing current I know. So from here magnetic field intensity H is equal to the number of the turns multiplied by magnetizing current. So divided by length of the conductor or core. Okay, LC. So this is the magnetic field intensity. Okay, in these conductors or core. Okay. So we know that according to Biot-Savart's law. So we know flux density is equal to how much amount of the flux density. So that is the B is equal to the nu H. So where nu is a, this is the according to Biot-Savart's law, where B is the flux density, right? Okay, this one is the flux density, the density here, where H is the, okay, this nu is the permeability of the core or permeability of the magnetic material, and where H is a magnetizing force or magnetic field intensity. Okay, all of you got it point? Magnetic field intensity. So now here we know that H. So let us assume. So this equation is a 1. Okay. And this equation is the second equation. So now from 1 and 2 equation, or substitute the equation 2 in the equation 1. So we get, okay, this is the we get. So that is a B is equal to, where B you can write the flux by area of the core. Okay. The is equal to permeability, where H is equal to number of turns multiplied by the which current here? Current required to create the flux. That's called magnetizing current. So divided by L, okay, L, this is the length of the core. So next one. So simplify here. So where flux is equal to, okay, this flux. So permeability, number of turns, magnetizing current, area of the core divided by length of the core. So next one, from here you can write flux is equal to, so this is a number of turns multiplied by magnetizing current divided by, so this is the length of the core divided by permeability into area of the core. So what we conclude here, so this number of turns multiplied by current, so it is nothing but MMF, okay, magnetomotive force. So this is a length and permeability area of the core. It is nothing but the reluctancy of the core. Reluctance of the core. Okay, MMF set of reluctancy of the core. So therefore we can write the flux phi of T is equal to MMF divided by the reluctancy of the core. So this is the flux relation. The flux is, okay, that's why I have written here directly. So whenever transformer is excited with the AC supply, time varying nature of the current passes through the winding turns. As a result, MMF setup and thereby flux will be created. How does flux create in the winding? This is the exactly procedure. According to Ampere's law, whenever a current carrying conductor produces magnetic field around it. So this, according to this Ampere's law, we can get, so here flux is equal to MMF by reluctance. Okay. Okay, all of you clear? Is that clear, everyone? Yes or no? Okay. So now we will discuss about how does EMF induced in the transformer windings. So we have a question. So that is how does flux produce. So next one, how does EMF induce in transformer windings. So in case of the primary winding, see. So in primary winding of the transformer, okay. So there is a, according to Faraday's laws of electromagnetic induction, V1 of T is equal directly proportional to the d psi by dt. Okay, where psi is equal to, okay, in this case, the psi is the number of turns of the primary winding multiplied by flux of the primary winding, flux produced in the primary winding. So phi of T. So now simplify here, this is a V1 of T is the directly proportional to, so differentiation of the flux linkage N1 the into phi 1 of T, okay, phi 1 of T, so dt. Got it? N1 is a number of turns, it is a finite value, so that here E1 of T is equal to minus N1, so d phi 1 of T, so dt. Okay, so this is the EMF induces in terms of the number of the, okay, in, so EMF induced in the primary winding, so in terms of the, here in number of the turns, okay, in the form of number of the turn. So this equation you can rewrite, okay, this equation can be rewrite, okay, like, so this equation the can be written as, okay, as below. So how do we write? See, the V1 of T is equal to, so this one is a minus of, okay, d psi by, okay, dt, okay, this one V1 of T, so is equal to minus d psi by, so d I nu magnetizing current multiplied by the this differentiation of the magnetizing current with respect to the time. So what about here? This current is a current flows in the primary winding only. So therefore here V1 of T is equal to, so this the minus, okay, self-inductance, okay, self-inductance of the winding, so multiplied by the differentiation of the current with respect to the time. So that's why this EMF is known as the self-induced EMF. Self-induced EMF. Okay. So now similarly in the secondary winding, how does EMF induced in the secondary winding of the transformer? So whatever flux produced in the primary winding also links in the secondary winding. So we know that, we know the flux produced in the primary winding, in primary winding, and also links in the secondary winding through transformer core. Got it my point? The flux is produced in the primary winding but links in the air. So therefore flux links in the where N2 is the number of the turns in the secondary winding. Okay, number of turns in secondary winding of the transformer. So where phi there is no flux in the air, there is no flux production in the secondary winding, only primary flux. Okay, this flux links in secondary winding, primary flux links in the secondary winding through transformer core. So according to Faraday's laws of electromagnetic induction, so that is the Faraday's laws of the electromagnetic induction. So here EMF induced directly proportional to which EMF? EMF induced in the secondary winding. So directly proportional to d psi by dt. So therefore here V2 of t is equal, is equal to minus N2. So d phi of t, okay, which flux here? Primary flux of the transformer. So this is the EMF induced in the secondary winding of the transformer. But what about EMF? This EMF, this equation you can write. So V2 of t, so is equal to minus the differentiation of the flux linkage. So with respect to that, there is no current in the secondary winding till now. So they under no load condition. So that which current here? Magnetizing current. So V2 of t is equal to the minus the d psi by the dt here. So d psi by the differentiation with respect to the current. Again current is the differentiation of current with respect to the time. So now simplify here, current flows in the other winding, so which is magnetically coupled. So that's why this EMF is a minus m, so di nu by dt. So this m is a mutual inductance and this EMF is known as the mutual induced EMF. So that what we conclude, EMF induced in the primary winding is a self-induced EMF of the transformer, and EMF induced in the secondary winding is mutual induced EMF. Okay. All of it clear? Is that clear, everyone? Yes or no? So now we have a questions like, so one of the question in the computer exam, so EMF induced in transformer is dash. So options are given like option A, the statically induced EMF, okay, and option B, dynamically induced EMF, and option C, self-induced EMF, and option D, mutual induced EMF. Okay, what is the answer for this question? Nature of the induced EMF in transformer. Nature of induced EMF. Nature of induced EMF in the transformer is, that is which one? EMF induced in the transformer is statically induced EMF. So what is the meaning of statically induced EMF here? EMF induced in a coil. EMF induced in a coil or winding due to relative motion. Relative motion between, relative time variation between magnetic field and conductor is called statically induced EMF. Okay, this is one of the question. So there is a here dynamically induced EMF means EMF induced in the transformer, EMF induced due to relative motion between the magnetic field and set of conductor is called dynamically induced EMF. So this is the option A is the correct for this question. And similarly, let us discuss another question. EMF induced in primary winding of the transformer is dash. So what is the answers options given for this question? Option A, statically induced EMF. Okay, option B, dynamically induced EMF, and option C, self-induced EMF. Okay, and option D, this the mutual induced EMF. Okay, here mentioned that some winding, primary winding of the transformer. The EMF induced in the transformer, here transformer is a statical induced EMF. But this statical induced EMF are two types. One is the self-induced EMF, okay, induced EMF, and second one is a mutual induced EMF. Okay, suppose if question is given like this, EMF induced in the primary winding of the transformer. So what is the answer for this question? So that is the self-induced EMF. Okay, so EMF induced in the primary winding of the transformer is a self-induced EMF. So how do we define this self-induced EMF? So EMF induced in a coil or winding. So due to current passes through its own. Due to current passes through its own winding or its own is called the self-induced EMF. Just like E1 is equal to minus L1 di nu by dt. So this current is a flows in primary winding but not in the secondary winding. So that's why it is treated as a self-induced EMF. Okay, and next another question. Third one. So EMF induced in secondary winding of the transformer is dash. Okay, so we have a same options. Option A, self-induced EMF, and option B, mutual induced EMF. Okay, and option C, statically induced EMF, and option D, dynamically induced EMF. Okay, so what about the here? What is the answer for this question? So EMF induced in the secondary winding of the transformer. So that is the E2 is equal to the minus, okay, N2. So d phi of t, okay, phi 1 of t dt here. So this equation you can write, okay, E2 is equal to the minus n, okay, here the n differentiation of the flux with respect to the time. So now here E2 is equal to minus, okay, this value is a the E2 minus, so differentiation of this current, the differentiation of the flux linkage with respect to the current, so multiplied by differentiation of the current with respect to the time. So which current here? Current flows in the primary winding. So this is called, we can represent E2 is equal to minus M, so d I know by the dt. So where M is a mutual inductance, where E2 is a mutual induced EMF. So that how do we define here? EMF induced in a coil. Induced in a coil. So due to EMF induced in a coil, due to current passes through another coil, passes through another coil, so which magnetically coupled through the same coil, magnetically coupled, okay. So this type of EMF is known as the mutual induced EMF. So this is also one more question. And next one, so it was previous the transco question. A single phase 50 Hz transformer has number of turns of 100 and 200 in its primary and secondary winding respectively. So variation of the flux with respect to time is given. Phi of t is equal to minus 0.05 t square minus 2t Webers. So EMF induced in the secondary winding will be in volts. Anyone can answer this question? So here given that, given phi of t, flux phi of t is equal to minus 0.05 the t square minus 2t Webers, right? So let us simplify this. Minus 0.05 the t square, the minus is the plus 0.1 t, okay. So this is the flux here. We know that EMF induced in the secondary winding. So EMF induced in the secondary winding, V2 of t is equal to the minus N2. So differentiation of the flux phi of t, the differentiation of flux with respect to the time. So now substitute here. So this is equal to minus here number of turns in the secondary winding 200. Okay, this is a differentiation of minus 0.05 t square, okay, plus 0.1 t, okay, differentiation with respect to the time, okay. So now this value is equal to minus 200, okay, into, okay, this is a differentiation with respect to the time. So now it is a 2 into, okay, minus of the 2 into 0.05, okay, plus, okay, 0.1. So this is the 2 into the t here 0.2. So therefore we can write directly also. So it is equal to minus 200, okay, upon this one is the 0.1 t, the plus the 0.1. So now here this is equal to the minus sign. So here is a 20 t plus 20, right? Plus or minus, there is a minus 20. So now simplify here. So that is the 20 into t minus 1. So all of you clear my point? So V2 of t is equal to the 20 into t minus 1. Okay. So there is a one more question. It is a very important. So if the transformer is excited with the AC supply, is excited with the square wave voltage source, then the shape of the induced EMF will be. So how do we answer this question? So here excited with a square wave. Okay, square wave means, okay, this is a non-sinusoidal periodic, periodic function, like the periodic waveform. So it is a time varying function only, non-sinusoidal but periodic nature. So transformer is excited with the square wave voltage source, then the shape of the induced EMF. So we know that here this is the transformer is a pure inductive nature, right? The transformer is the pure inductive nature. So here voltage across therefore the voltage across the inductors, that is the source voltage. So we know Vs is equal to the L, okay, d I nu by dt. Okay, d I nu by dt here. So from here we can write the magnetizing current is equal to, okay, this magnetizing current is a 1 by L integration, so Vs, okay, dt here. So this is the nature of the magnetizing current. So that is a I know is equal to, so 1 by L Vs dt1. So after getting the I know, then we can find out EMF, the nature of the induced EMF, So that is a V of t, okay, V is equal to the minus L, okay, into the differentiation of the magnetizing current with respect to the time. So these two equations are enough to answer this question. So here given that the transformer is excited with a square wave, okay, given here square wave voltage source. So here given nature of the supply, okay, given that the Vs is the square wave, right, the square wave. So next one, if let us find out nature of the magnetizing current. I know 1 by L, okay, integration of the square wave with respect to the time. So with respect to time here. So when integration of the square wave is that is a integration of the square. Okay, this we will get triangular wave. Okay, next one, we require nature of induced EMF. So where E is a directly here, V is equal to minus L, the d I nu by the dt. So it is equal to minus L differentiation of the triangular wave with respect to the time. So here we get the integration and differentiation, so that you will get same wave. So it is a square wave, or sometimes it is also called the pulsed wave. Am I right? Okay, this is the pulsed wave. So that answer for this question here, the square wave only. Okay, if the integration and square wave. Okay, and next one more question. The transformer is excited with a square wave current source. Okay, square wave current source. Previously in this question, transformer is excited with a square wave voltage source, then the shape of the induced EMF. So same question, the transformer is excited with a square wave current source, then the shape of induced EMF. Option A is given sinusoidal wave, square wave, impulse wave, and triangular wave. Okay, so how do we answer this question? So we know that here given is a magnetizing current, I know. So that is the square wave. So got it? So let us find out shape of induced EMF. So E of t, okay, that is equal to minus L, okay, differentiation of the magnetizing current with respect to the time. So therefore V of t is equal to minus L, the differentiation of this square wave with respect to the time. So differentiation of the square wave, it is a impulse wave. Impulse wave. Okay. So that what is the answer for this question? The impulse wave. Next. So one more question based on the same concept. So if transformer is excited with triangular wave voltage source, then the shape of induced EMF. So here given that square wave with 90-degree displacement, square wave with 180-degree displacement, the triangular wave with 90-degree displacement, triangular wave with 180-degree displacement. So here given, so Vs is a triangular wave, right? So first let us find out the shape of the magnetizing current. So that is a 1 by L integration Vs dt. So that is equal to 1 by L integration the triangular wave with respect to the time. So integration of the triangular wave, you will get parabolic wave. Okay, parabolic wave. So now we required shape of the induced EMF. E is equal to minus L d I nu by dt. So this is the minus L, okay, differentiation with respect to the time. Differentiation of the parabolic wave. So with respect to the time, so that you will get again same wave. So that is the triangular wave. But we have a two options: triangular wave with 90-degree displacement and triangular wave with 180-degree displacement. So here is a voltage, the relation between the supply voltage and induced EMF. Always E the lags the applied voltage by 180 degrees, right? That's why transformer is treated as a 180-degree phase shifting device. So answer for this question is triangular wave with 180-degree displacement. Now similarly, one more question based on the same topic. So if the transformer is excited with a triangular wave current source, then the shape of induced EMF will be. So how do we answer this question? Here given waveform is a triangular wave with current source. So that given here, the shape of magnetizing current is a triangular wave. Okay, got it? So now we required shape of the induced EMF. How do we obtain shape of induced EMF? What is the relation? The shape of induced EMF is equal to minus L, the differentiation with respect to the time. So now this is equal to minus L differentiation. So with respect to the time, the differentiation of the triangular wave, with respect to the time. So that it is equal to the square wave. Okay, square wave or pulsed wave or step wave. So this one is a, what is the relation between? So EMF and this is the magnetizing current. So magnetizing current here I nu is equal to Im sin omega t. Let us assume. Okay, and flux is equal to that is a flux is the N into I nu. Okay, that is equal to similar pi maximum sin omega t. So therefore E is equal to minus N, so d phi by dt. So this value is equal to E maximum, the sin omega t minus pi by 2. So that what is the relation between? So E lags the I nu by 90 degrees. So that answer for this question is the square wave with 90-degree displacement. So here we have a question, any type of the wave is given. So integration of the impulse wave. So that is a square. Okay, integration of the square wave. So it is a triangular wave, and integration of the triangular wave. So that is a parabolic wave. Okay, and here E the phase displacement between the V and applied voltage Vs. So that is the 180 degrees. The phase displacement between the V and magnetizing current is a 9. Sometimes the question given in the given waveform is a voltage or given waveform is a current. So by using this you can answer these questions. Okay. So these are the place batches taken by the top educators for EEE and EC. One is a target ESE prelims 2021. Another one is rank booster batch for the GATE 2021. So evaluate batch for the GATE 2022 for EC students. which is in English and Hindi, which was starts on 21st December. Some of the top educators are taking these batches. Another batch, evaluate batch for the GATE 2022 electrical batch A, so which is in English or Hindi, and which was starts on 21st December. Some of the top educators are taking these batches. So it is an official Creatrix channel. Please join in this group, and it is Unacademy GATE English channel. So these are the different type of channels under the Unacademy: Creatrix GATE Mechanical, Creatrix GATE Electrical, Unacademy GATE the Civil, Unacademy GATE English, Unacademy Computer Science, Unacademy GATE Questions, Electrical Junction. Thank you all. Thank you very much.